So we're going to wrap up with Van Parunak, who was on a different team, along with Scott Page, who was just mentioned at the University of Michigan. Van is a senior scientist at SoarTech based in Ann Arbor. He has a very broad range of research interests, including swarm intelligence and natural language. And today he's going to tell you about the team that he was involved in for the IARPA contest.
Thank you very much. Is Scott here? Oh, okay, so if I tell lies, if you ask hard questions, I can't call on him to answer them. I want to talk to you about work that we did when Jason showed the teams that were involved. I was listed as with Jacobs Technology, which was the team that proposed this project. Most of the way through, our technical people moved over to SOAR technology, and so we ended as a SOAR project. But Jacobs gets some credit here for initiating the project. Team members with us were SRI, Digital Sandbox, Scott Page, of course, Answer Corporation, and Mercyhurst College. The main theme that I want to make with this presentation is that the exercise of forecasting is intrinsically bound up with the models that forecasters have in their heads, what Lyle called a partial information theory. Different people are attending to different things, and these things may be structured in different sorts of ways. So I want to explain to you why forecaster models are important, and then if they are important, we have to do two things. We have to be able to estimate how similar or dissimilar those models are. And then if we have some measure of similarity or dissimilarity of models, we need to be able to account for that and use it in the aggregation process. We called our project Informed, Interrelated Forecast Reflecting Models Behind Experts' Decisions, based directly on Scott's work. The idea was that the standard ULINOP approach does a credibility-weighted averaging over forecasts. We wanted to try to take into account the knowledge that people had and leverage that in the aggregation process. Lyle mentioned to you the work on generated versus interpreted signals. I'd like to go into a little bit more depth here. In a generated signal view of the world, the fundamental model is a physical sensor. Each data source estimates the target value as what the true value is plus some independently selected, perhaps source-specific error term. And you report yes if the value you come up with is greater than some threshold. So think of a physical sensor here. In this world, the answers you get from your sensors are statistically independent from one another, conditioned on the true value of the question. And the more points you get, the smaller the standard deviation gets. You're right smack in the middle of the statistics that we all know and love from our basic physics classes. With interpreted signals, each source is attending to a set of source-specific features in the information. And that source, that forecaster, reports yes if those features are satisfied. The prototype here is that the forecaster is executing some mental model. In this world, the answers are not independent. In fact, they are guaranteed to be negatively correlated, conditioned on at least one outcome of the problem. This is the reason behind Lyle's statements that you cannot average interpreted signals, because the fundamental assumption of independence of those readings on which all of our classical statistical methods rest is not valid, provably not valid, and Hong and Page's paper is central to this. Here, it's not more forecasts that get you more accuracy, it's more variety of forecasts to ensure that you cover that partial information space, to make sure that the blind spots of one forecaster are filled in by what another forecaster is attending to. We wanted to think hard about this, and so we did some reading in the psychological literature to understand what might be a credible mental model. We were quickly drawn to the work of people like Phil Johnson-Laird and Dan Kahneman, and in particular Kahneman and Tversky's idea of a simulation heuristic. There's a good deal of evidence that when people think about problems, they're actually running a sequential causal model of the world in their minds. They're not running a Bayes net. We know that. That don't correlate well with what a Bayes net gives. They're thinking causally. So we constructed as an ansatz for the mental model to guide our thinking a narrative structure. And that's symbolized here by these little graphs here. I'm going to show you this thing. Do not point in your remaining good eye. OK. These are meant to be little causal graphs going up here. The data that we have a set of forecasters, we have a set of problems, and we have hopefully repeated forecasts from people through time. There's one of the forecast questions. That was not one that we answered. We answered this question with earlier years associated with it, when those years were still valid. Now think about the patterns of responses that we have here to these three questions. If you were just averaging things together, you might think, well, here the answer is obviously no, and here it's obviously yes, and here it's obviously yes. But these are not the same situation. Here, if forecasters B and C both have the same mental model, if they're both attending to the same things, is this really 2 over 1, or is this 1 against 1? Is it? Because they're thinking about it the same way. They're really attending to the same information. Now, if I go over here, what's the story here? The story here is that these two people who have the same model are giving different answers. What's that say about their model? That model does not really apply to this particular question. It doesn't give me any purchase. So they're not really giving me any information. I should be simply attending to that model. Hopefully there's some others here as well that I could combine in with that. On the left-hand example, this is very valuable. Here are 2 different models that give me the same answer to the question. So I really want to pay attention to what those fellows say. So here is an example of the ansatz that we created. We had intelligence analysts draw up for each question a causal space in which the nodes, there's a specific formal definition to these nodes. These are statements about the world to which probabilities could be assigned. They're the same stuff that you would have in the nodes of a Bayes network. However, the links between them are quite different from a Bayes network. The links between them represent time-ordered, narratively coherent transitions, roughly causality. So we have a start node, and we have possible outcomes. This is the Assad question. And any path through this is a story of how it might come about that Assad would be either in office or out of office by the target date. You can imagine transition probabilities on these edges, saying that if you're here, what's the likelihood that you might go to here or to here? That transition probability is going to be a model of the subjective tendency of a given forecaster to make that move. The model includes the possibility for inhibitory links. We allow the attachment of evidence, news stories, to individual nodes. So when something comes out in the paper that says, oh, this supports that particular statement, that can be attached to the model. And then a dominant path through this would be a particular trajectory that leads to that outcome. This is greatly reduced so you can read the labels. Here is the actual Assad graph. It's much larger, much more complex. And here's an example of our log of news events, also curated by intelligence analysts and linked to specific nodes in that model. So our background hypothesis here is that the mental models that people are executing are something like a structure like this, a narrative graph. What they're doing is they're telling themselves stories, and that determines the numbers they assign at the other end. If that's true, there's a good reason for the lack of calibration that Phil Tetlock has been noting for years in probabilistic forecasts of future events. And that's because those numbers probably aren't probabilities. They're probably metrics on an underlying narrative space like this that reflect things like, oh, how many possible narratives could get me to this result? The more stories I could tell that would get me there, the higher number I'll give it. Or how long is the story? The more direct the story is, the higher number I'll give it. Or how coherent is the story? Yeah, I could put a story together, but nobody would believe this particular link in it. So maybe these things are not really probabilities after all. Okay, so we think that that's how people think. How can I estimate against this kind of an ansatz the degree of similarity among different people's mental models? And then how can I use that in aggregation? We treated this somewhat along the line of the Cheshire Cat in Alice in Wonderland. You remember this cat that slowly disappeared piece by piece? So we started with the full model and did some experiments with that. and then we worked our way down, eliminating successive pieces of it. With the full model, we looked at the links to nodes, the evidence associated with those nodes. We had the forecasts, and what we did was we fit transition weights to each forecaster to determine which paths through the model they were probably using in coming up with the assignments of numbers to the outcomes. So we have spectrums for different forecasters, and now we can compute an information geometric divergence among those spectra as a measure of their distinctness. We see a signal, but there's poor replicability, there's lots and lots of noise in it, and it's really, really expensive to construct these models and manually curate the evidence against them. We have some ideas for ways to construct models like this automatically, to crowdsource them, but that was not part of our tasking on this particular project. That, Jason, is a research idea for future activities, and by the way, it's part of one of the RFIs that you and some of your colleagues are looking at. So the next step is to say, well, let's forget the nodes and the links. I have evidence that's been lined up with specific IFPs. Or maybe what I could do is look at the date that that evidence showed up and correlate that with the date that a forecast was made. Now, there actually is a pretty good signal here. The idea is that when a news event happens that aligns with my mental model, I'm more likely to log on and update my prediction because I just learned something that's relevant. If you're not paying attention to a path in the narrative space that is relevant to that particular event, nothing has changed. So we look for the correlation between the events and when people issue forecasts on a per question basis. This has a very nice signal that simply for reasons of time, we did not have a chance to study further. It does require some kind of repeated forecasting. Another idea was to say, well, forget the association of evidence with IFPs. Just look at when events happened that are relevant to any of the problems and try to correlate that with the forecast. That didn't work well at all. People tended to go in and update forecasts, most of all, when new problems were issued, not when events happened in the world. This is, in some degree, an artifact of the structure of the program, and might not be the case if you had analysts looking at longer-term questions that weren't being introduced every week, a new set of questions coming out. But I would not pursue this. This definitely merits further pursuit. The next step is to take away even the evidence. So now we've done away with the narrative model itself. We've done away with the evidence. We just look at the forecasts themselves. I will amplify on this a little bit more. And this we have studied in quite a bit of detail, and we believe it offers considerable promise. We also thought, well, maybe we could just look at who answers which questions. Because if two people tend to answer the same questions, it's probably because they have models that accommodate those particular questions. And there is some promising signal there, but again, it's not one of the things that we put resources into. So let's talk about how we can estimate forecaster diversity just from the forecasts themselves. So here are my forecasters with different individual forecasting problems, the IFPs. And I've sort of drawn a cartoon here of their distributions for each of these IFPs. Now, on a pairwise basis, I could use an information geometric measure of divergence among two forecasters' distributions to get a measure of how distinct forecasters I and J are on problem A. That's a within IFP pairwise user diversity. I could average those to get a cross IFP pairwise user diversity. So how different are two forecasters within the same problem? How different are they measured across all problems? Think about those two numbers. If two people differ on many problems, they differ across problems, they're probably working with different models. If they have the same model, they tend to answer the same on all the problems, and they'd have a low CID, cross information diversity. If they differ on many models, but they agree on this particular question, then I've got people with different models thinking the same answer on this question, and I ought to be able to leverage that. And there are a number of ways to put that together. A simple thing is to take a ratio. Here's the cross number. Here's the within number. You add a small number here to avoid division by 0. It's important to do this pairwise. We found that if we average out across one person's relation to all other forecasters, a lot gets lost in the averaging. So it's best to look at pairwise comparisons of people on this basis. We can take this ratio and normalize it to stay within a 0 to 2 range. Then you get an equation that looks like this. You can use those within problem divergences with a velocity measure. Find forecasters who forecast repeatedly, who start far apart but move together over time. The starting far apart suggests they have different models. The fact that they come together suggests those models are leading them to a similar outcome. Here's a little picture of how this idea works out. This is one particular forecasting problem. I must confess, Jason, I didn't memorize all the numbers. I don't know what the problem is. Maybe you do. And each point is a final forecast from one forecaster. So here's the within IFP diversity from about 0.5 up to 2. Here is the cross IFP diversity down here. And up this axis is the Breyer score. And we've plotted each forecaster's point, which is here an average of that forecaster compared with all the others. Here is the worst performer. The highest Breyer score has high within problem diversity as well as high cross-problem diversity. Different models, different results everywhere you go. Next, we move over a little ways. As the CID drops, as the cross problem diversity drops, there is a little bit of improvement, but the real improvement happens here as the within IFP diversity drops. And then, as cross-problem diversity begins to increase, we get the best performance over here. And we've done a number of empirical experiments with this measure, and it does give us some benefit, something on the order of 5 to 8 to 10%, depending on the particular configuration. So I've got some ways now that I can measure diversity. How can I take advantage of that in aggregation? Well, Lyle has talked about different ways to combine these forecasts. And he's mentioned that if I give each forecaster a weight, I can average the forecasters together. That's what the unweighted linear, what a standard averaging method would do. But averaging is not valid in this situation because we have interpreted signals and not generated signals. So here is a voting description. We'll take the set of forecasters who favor a particular outcome, and we will only sum over those forecasters with whatever the weight is that we choose to give them. Here's an example. Let's say we have 5 opinions, 0.95, 0.95, 0.45, 0.45, 0.45, all the same weight. Averaging would say the answer is 0.65. So you'd say, yes, the event is likely to happen. It's above 0.5. But if you vote, it's 2 out of 5 for the event, or 0.4, which is false. Notice also that 0.4 is lower than any of these individual opinions. And that's an important characteristic of voting. Individual forecasts, here's a 3-way question. It could be 1 for the first option, 100% for the second option, 100% for the third option. Every forecast is going to be somewhere within that simplex. And the forecasts themselves define a convex hull within that simplex. Averaging methods, as long as the weights are non-negative, necessarily are constrained to the interior of the convex hull. Voting can move you outside of the convex hull. And now here's another theorem, again due to Scott and Lu Hong, part of a paper that we wrote jointly on this work. The optimal aggregation of generated signals lies within their convex hull, but the optimal aggregation of interpreted signals may fall outside the convex hull. And for a simple but very straightforward example, that is a theorem, and you can read about it in the reference paper. Now, there are a number of ways you can mix and match these. I'm not going to go through these today. Here are different ways of measuring diversity. Here are comparing weighting versus voting schemes. How do you combine pairwise diversities? I've mentioned that you lose information if you just say, here's this forecaster's diversity with everybody else. That's not really a useful number. It's best to do some kind of a pairwise measure, or to take pairwise measures and cluster them up a hierarchy using aggregative clustering. We've experimented with all those and report some of the results in a paper that's available. Final lessons. The first is mental models matter. You see this in 2 ways. First, you see it that voting dominates averaging, suggesting that forecast opinions are interpreted, not generated, but I'm going to make a comment about that a bit later. Second, we see that they matter because of the effectiveness of using cross-problem versus within-problem pairwise diversities. That's a tractable way to estimate diversity without having to construct an explicit model. Those two don't work well together. And there are reasons for that that you can read about in the last paper that I referenced. You get strong results from each of them separately. Mixing them together doesn't work. They're attending to different things. The next observation is that model-based aggregation cannot overcome lousy forecasts. Garbage in, garbage out, and I think that was the great triumph of the good judgment team, was to show that whether you use training to improve people's skills or whether you put them in teams so that they can hold one another accountable to their forecasts, that kind of effect is very important in getting good results out of an aggregation method. You've got to give it good input. And we're very gratified that Lyell's able to take some of the methods that we developed, the voting in particular, and apply to their data, improving their results even further. If you think about it, a lot of the aggregation is going on in those teams as people interact. It's not being done mathematically. It's being done in the team. But the third thing that I want to call our attention to is that there's good evidence, and here again Dan Kahneman comes to mind, that there are multiple levels of reasoning. There are very fast, intuitive methods that people use, and then there are deeper, more reasoned methods. And I think Scott would agree that the notion of mental models and generated signals is probably more appropriate to what Kahneman calls System 2 than it is System 1. System 1 is more of a gut-level reaction. It's more compiled down. It may even be driven by limbic issues if you're dealing with emotionally sensitive questions. And I think we have to think about when one applies model-based methods, partly in terms of, are we getting people to engage System 2? Certainly training is one of the things that can get people to engage System 2. It'll say to them, I don't care what your initial response is, stop, think about this, go through a disciplined process. And in that case, I would expect to get even more leverage out of the model-based methods. Thank you.